Happy Halloween. Unlike Andrzej, I didn't dress up. I was under the impression that dressing up as a regular professor that is teaching Rademacher averages will be scary enough. Okay, so let me recap what we did. Last time we talked about empirical risk minimization. That's denoted by f hat n. And this is an empirical risk minimization over some class f of functions. So we're out of this class of models. We're picking one with the smallest empirical risk, the best fit to data, right? So that's ERM. And now you can ask. This was our goal, right? To establish a generalization performance, right? This is the expected loss on the future data of this of this algorithm, right? Now we're going to compare it to the best you could have done if you knew the distribution underlying the data, which is the f sub f. The best you could have done within the class f, right? That's the minimizer of the expected loss. And what we said is there's a simple kind of add a couple of terms and then cancel a couple of terms analysis that gets you from here to this object. Now this object is going to be the object of study for today's lecture. Now imagine that you knew how to deal with this guy. Here there is no algorithm. The algorithm is gone, right? We remove the hat, we remove the dependence on the on the algorithm, on the data, and so the only thing that we used in making this step is that the algorithm was minimizing the empirical fit to data, right? Empirical loss. So for any empirical minimizer over class F, this is going to be a true inequality. So suppose you could say that this object is 1 over square root of n. That's it, right? Then you've established that there is a certain, it's called the sample complexity bound, right? You've established that to get an upper bound of epsilon on excess loss. By the way, I never use this, but this is called excess loss. It's the loss access to the model F, right? To the class F. So this is called excess loss. So expected excess loss, thank you, is. Can I keep your sword? Expected excess loss is bounded by epsilon as soon as epsilon is as soon as n is at least 1 over epsilon squared, let's say, right? So that would correspond to showing that this is 1 over square root of n. N is the size of the sample, right? Everyone is on the same page, right? So the whole game is get upper bounds on this guy, right? If you know how to deal with this guy, I'm happy because you've learned kind of the important statistical learning part of this course, right? Yes?
The expectation on the right-hand side is the sample you're getting?
It's over the data, yes, over n pairs. So there's a convention, which is if I just write expectation without anything, then I'm tacitly assuming that it's expectation over everything that's random about this guy. So what is random about this guy? This is non-random, right? Remember the first lecture we put down a bunch of things? For a fixed f that doesn't depend on the data, this is not random, right? This one is random. And what is the randomness? It's exactly the data set, right? Because it's the empirical L hat, it depends on all the data. So we're taking expectation over the data. Good. And sometimes I will put a subscript to indicate exactly what we're averaging over, right? Another little thing is, to be precise, this shouldn't be max, this should be supremum. I'm not going to bother. Well, maybe sometimes I will slip and write a sup. But just think max, okay? You don't need to worry about the achievability of max. if you're worried about the achievability of max at a function, then you write a sup, right? Okay. I feel that people get more scared about the sup than about the max. So max is somehow easier. So what we're going to do today is we're going to show that there is something here, which is called random macro averages, which actually makes it very easy to analyze or get actual bounds, okay? So you can, hopefully if you understand what I do today in this lecture and you do the homework, you'll be able to prove sample complexity bounds of at least simple classes, right? So this should be a kind of a back of the envelope calculations from this point. Now I'm going to talk about this object here that I will describe, but then if you want some other quantities that even further upper bound this object, that's a VC dimension, covering numbers, chaining. I'm not going to talk about those, or I'll briefly mention, but all of them are upper bounds on this object. And for some of them, it's much easier to compute this upper bound. It might be looser, right? More loose because we're going to an upper bound. But it might be easier to get, right? So for instance, for half spaces, you immediately say, VC dimension is D, and so I can get an upper bound here, okay? But really the kind of the object which doesn't really lose anything against this, it's essentially an upper and lower bound, unless you care about the curvature of the loss function, and then, okay, we can talk about that separately. So for all intents and purposes, this is kind of the best object to consider, okay? And it's weird to talk about this object without naming it, but it will be macro averages, okay? Okay, I apologize. Okay, so let me spend just a couple of more minutes to explain why this object is not too trivial, right? I can write it as follows. Maybe it will make it simpler to understand. First of all, I'm gonna work with a class G, and really I'm thinking of G as a loss composed with a function f, right? So I'm thinking of this G of z. That's the same as a loss of f of x comma y, where z is x comma y, right? So I want to abstract for now. I'm going to abstract away the fact that there is even a loss function, right? I can just say there's some function g. And what I'm looking at is the expected max over g in g of expected g of z. So z now is a random variable instead of x comma y, a random variable, minus the 1 over n sum of g of zi. Right? So now the data, if you wish, I mean, we don't have to actually think about data anymore. It's just a collection of random variables. Is z1 through zi, z1 through zn. And this expectation is over z1 through zn. Everyone is okay with that? Good? Okay, now let me just visually simplify things. Let me think of expected max of a random variable u, which is indexed by g. So think of u1, u2, u3. Let's say I enumerate all the elements of g if it's enumerable, if it's countable. Where, of course, ug is this thing, right? I mean, I haven't done anything. Okay, so UG is a zero mean random variable. Is everyone clear about that? It's a zero mean random variable, right? Because if you take expectation of U, you get zero, right? It's centered. Expectation of this, they're all the same. It's this guy, so the mean is zero. Is there anyone who needs further explanation? No? Okay. And by the central limit theorem, kind of the typical fluctuations of UG are what? How high, how low does it get? Can it be negative? Of course, it's a zero mean, so it goes up and down. But what are the typical kind of fluctuations? What's the size of typical fluctuation? From the central limit theorem? 1 over square root of n, right? Okay. So typical fluctuations are of UG are 1 over square root of n. I'm putting it in quotes because this is not a precise statement. Okay. But now you see, I have a. Now I'm going to do the visual explanation. So this is my one of the random variables, and it has a distribution. This is 0, and it goes up and down on the order of 1 over square root of n, right? This is my. Let me erase this. This is my UG1, and then there is another one. Another random variable, the distribution of that is roughly Gaussian, right, by the central limit theorem. Let's just pretend it's Gaussian, and the width is about 1 over square root of n. And it also goes up and down, right? So now I have a collection of these. This is the collection that I proposed, right, UG. Now, one of these doesn't get too high necessarily. It stays around 1 over square root of n. Occasionally, with small probability, it might get a little bit larger, right? But now when I look at several, and I look at where's the maximum of these, well, that's already a little bit higher, right? Because, you know, think of flipping a coin. Heads is 1, tails is -1. So I get +1 or -1 with probability 50-50. What's the expected value? 0. But now what is the expected value of the maximum of 2 coins? That's no longer 0, right? I have to consider 4 cases, right? Both of them are minus, that's probability 1/4. One is up, one is down, that's probability half, symmetric. And then the probability that they both get up to 1 is 1/4. So now the expected maximum is already larger than 0. You see that? And so just from the fact that there are many of these, and let's for a second say that they're independent, because they all oscillate independently, you know, sometimes one of them goes up, and then we count it. As soon as one of them goes higher up, we count it, right? We look at the maximum. So the larger this collection is, the higher is the expected maximum. Is that point clear? Yeah? Okay. Now, the situation becomes more tricky because these are not independent. So what happens if they're not independent? Imagine that they're completely dependent. They all go up and down at the same time, right? That's what it means to be completely dependent, right? I mean, roughly speaking. Well, then it's the same as having one variable, right? So it's not really the number of them that matters, right? There is something more than just the number of them. You see that? And it really, it seems like a complicated thing, right? Because you have to take into account the different dependencies between these different U sub G. Is that point clear? If they're all independent, you know, the larger the number, the kind of the higher is the maximum. Right? It's the same thing with multiple hypothesis testing. If you come from statistics, when you do multiple hypothesis tests with the same data, you really have to slash your alpha value, right, or the p-value, because otherwise you just get spurious. Just by chance, you get some experiment that turns up statistically significant, right? So it's exactly the same idea here. Okay, so what we're really going to do is try to address this question: what is the behavior of this maximum in the presence of, you know, correlations? So where do correlations come from? Well, they really come from the correlations between functions, right? These are losses of functions, right? So if you've got two functions which are the same, their losses, L composed with F, are roughly the same. And so you would expect that they behave similarly, right? Now imagine trying to understand this for neural networks. You have these all neural networks. Are they all different? When you switch one weight in the neural network, do you get a completely different function? You don't, right? So we shouldn't just count the number of possible neural networks you can ever get. That's infinite, right? You should somehow see what are the really number of different neural networks, right? That's a rough sense. Have some kind of handle on that question. Okay, so this is intuition. Next, I'm gonna jump into a little bit more mathematics. Any questions about the intuition? If the class G contains one function, that expected maximum is 0, because they're all centered. As soon as it contains two functions, and these two functions are different, it's already 1 over square root of n. If they're sufficiently kind of separated from each other. And we'll make that precise. Okay, so let me erase this. Okay, so what I'm going to do now is I'm going to forget about functions. I'm going to think of sets. Okay, so from now on, I'm going to ask a question. Let G, and really that G is like a calligraphic G. I know how to do it. Let's see. This calligraphic G. And this one is just a regular latex G. Now this is going to be a subset of a hypercube minus 1 to the power n. Now forget about learning, forget about everything, right? This is just a subset of an n-dimensional hypercube. And you have some subset. And then what I want to ask is, what is the complexity of this set? So let's say this G looks like this. Right? So, so what is the complexity of this? This is a subset of, it lives in a cube. Okay, it lives in an n-dimensional cube. What is the complexity of this? Use my Russian accent. What is the complexity of this? of this object? Okay, so if this object, the subset, was countable, or let's say finite, what would be the complexity? Just a number of points, right? But that's a bad notion of complexity if it's kind of a continuous object, right? How about, so let's say it's not countable. So what would be a notion? What other notion would you suggest? Volume. Good. So maybe, count. So that's kind of bad because if it's uncountable, you can't count. Volume is another one. So that's an interesting notion. And it's not good because you see, if one dimension gets flat, what happens to the volume? It becomes 0. And then you have to look at the n-1 dimensional volume, but then it jumps, right? So it's kind of a strange notion that there's no continuity, right? So it gets close to 0. So should you be considering it as an object in n-dimensional space or n-1 dimensional space? If it's n-dimensional object, then the volume is very small, but it's still complex, so it's not a good notion. Yes?
What's dimension if it's a manifold?
Yes, so a dimension could be 1, but then we really cannot distinguish things of the same dimension. Yes, so dimension. Yeah, I mean it could be, but okay. For many of the cases we're gonna consider, it's not really the right notion. Okay, so here's the proposition. This is what I'm gonna do. So I'm gonna I'm going to take this poor guy and let's say this is the origin, and maybe this is the hypercube. And maybe I should center that poor guy, but again, it doesn't matter. What I'm going to do is I'm going to look at a random direction, and I'm going to measure how tall he is or she is. So in this way, I'm gonna get some kind of it's probably better if I center it just visually. It's going to be easier to visualize this. It actually doesn't really matter if you center or not. It makes no difference. But let me center it. Let me use a different. Okay. Sorry. Okay. So I'm going to measure a projection of that guy onto this direction. Right? I get a number. I look at a different one. Think of this as like an X-ray. What's the projection? Okay, this guy is the maximum, right? So that gives me the projection. Right? And now I'm just, in all the directions, I'm going to measure the distance, the maximum projection, right? How do I write this? I'm going to write it as a max over a, let's say, a vector nu from, let's say, from a sphere in n-1. Okay, so it's just a n-dimensional sphere, n-1. Nu. Oh, sorry. So for a nu from the sphere, I'm going to measure. That's the direction. I'm going to measure the right. That's exactly the largest projection I could obtain using my set, right? But now let me average over all the directions. So I'm gonna say on average. What is the projection? What is the average projection onto all the directions, right? Yes. It's not. So for the next hour, it's not calculated. Here, always G is going to be the subset. Can you guys see this green or question?
Why is it n-1 instead of s?
That's a typical way to denote a sphere in n dimensions because it's a n-1 dimension. Right? Okay. Now, let me actually, instead of a sphere, let me do a Gaussian, because Gaussian kind of behaves like a sphere, right? It's symmetric, right? So now I'm going to say it's the nu is a multidimensional Gaussian, spherical Gaussian, isotropic Gaussian. Okay? So instead of looking at the sphere, a Gaussian vector is going to be roughly like a sphere, right? It's going to live roughly in a sphere. So it's roughly the same concept. Okay, so this was our kind of A, this is our B. This object is called the Gaussian width. Gaussian width. It's a measure of width of this object, right? Is it clear what we're doing? We're picking a random Gaussian vector and then looking at how far this object projects in that direction, right? And it should roughly be a measure of the width of this object, right? Yes?
So what's the distribution?
If it's on a sphere, I'm going to think just a uniform on a sphere. and if it's isotropic Gaussian, is just, you know, n zero identity of
Yeah,
everything.
it's symmetry.
It's symmetric, yes.
So how is it symmetric when it's Gaussian? Like it's like
The Gaussian distribution is symmetric if you take.
yeah, but it's not like you do not put similar weight on different like.
Yeah, so it's slightly different, but you can mathematically relate uniform on a sphere to a Gaussian. You can do that calculation, it's actually simple. Okay? Yes.
So do you mean the angle of the V is Gaussian distributed or
No,
the
the vector itself, it's a vector, right? G is a subset of minus 1, 1 to the n-dimensional vector. And this one is an n-dimensional vector. It's a random vector with a Gaussian distribution.
So could you give an example of, say, it's just two-dimensional and you are...
Yeah, so if it's two-dimensional, there is a Gaussian. I don't want to spoil my... But you can think of a bump, right? A Gaussian distribution. I'm going to draw a vector from that distribution, and then I'm going to measure the projection onto that vector. And then I'm going to ask, what is the expected size of the projection?
So do you normalize the new vector before you take the projection?
Yes, so you have to carefully normalize by the square root of the dimension. But I don't want to spend too much time on it because I'm actually not going to talk about the Gaussian root. I'm going to propose something even simpler. Okay? Is that okay? Yes.
So this whole concept of this circular complexity thing, it doesn't count for the fact, like, for example, if your image, for example, in this case, has like very small perturbations, right? So theoretically, you would assume that that would increase the complexity. Because it has
Inside, you mean?
like just on the boundary.
On the boundary?
Like yeah.
I
extremely
think
small, like,
all of them take into account these small changes.
But in this case, like for if like there is a tail somewhere in this in some dimension, such that this it would just like wouldn't that come at the maximum and finds
So,
tail?
so I think what you were saying is really only the convex hull matters.
Yeah.
And that is true, because projection of a body onto a direction is the same as a projection of a convex hull of the body onto a projection,
Yeah.
and that's true. So this measure of complexity is insensitive to the teeth and the eyes and the shape. Okay, it really only cares about the convex hull. Yeah, it's actually going to be a good thing. Any other questions? Okay, let me not do. I just want you to know that it exists. I'm going to do a C. I'm going to take nu to be. Actually, I'm going to call it epsilon. I'm gonna take epsilon 1 through epsilon n. And I think this died, right? Yes. Minus plus, I can do it. Yay. Okay. Good. So from now on, epsilon I are what are called Rademacher random variables. They're independent plus minus 1 coin flips, probability 50-50. Okay? It's just Bernoulli, but Bernoulli is 0, 1, and this one is minus 1, 1. But it's the same thing, right? So Bernoulli, unbiased, but minus 1, 1. Any questions? So when I write epsilon, I mean, sometimes it will mean accuracy in our procedure, but you'll see from the context, epsilon is just a vector. Epsilon is going to be the vector of these plus minus 1. So in this picture, this epsilon takes on values in the vertices of the hypercube, uniformly at random, right? So there are 2 to the n possible values, and it takes on those values, and that's what I'm going to do. I'm going to look at expected over epsilon 1 through epsilon n, max of over g in g of epsilon, complexity of this guy only in the directions which are to the vertex of the hypercube. Okay, I'm gonna miss a little bit, a few things, so now it's kind of coordinate dependent, but it's gonna be the right thing in any case, okay? It's gonna be good enough for government work, okay? This is called Rademacher averages. Rademacher averages of G. There's nothing scary about this, right? People get scared from the name Rademacher average. It's just the width of that thing, right? On average, right? That's all. Right? Nothing to be scared about. Questions about this? Yes.
So, are you just choosing each epsilon I to be Bernoulli over positive one and minus positive one and negative one because your space is in -1 to 1? Or if you are, okay, so if there is a different space, you should choose another vector?
No, we're always going to use ±1.
Okay.
It's enough.
So even though the space is...
Yeah, so when we go to general G, it doesn't matter. ±1 is the right random variable. So this ±1 with probability 1/2 each is not tied to these guys. That's a good question because then you can think of kind of objects which are larger than this -1,1. They don't live in this -1,1 box, and that's going to be the case. But you still measure it in the directions, okay? Because it's only what's important is the direction, right? The direction is important, and then how far you go in that direction doesn't really matter. Yeah.
What's the solution as to why they use this vector as like unit vectors? Like
Unit like on a sphere.
Yeah.
You could, and they're all so essentially up to log factors. In many of the cases, they're equivalent, and sometimes even within a constant factor. So as a measure of complexity, you're not going to gain much. For learning, this is actually better in many cases than the Gaussian. Easier to. It's often easier to deal with, or you can just transpose into another one. That doesn't really matter. Yes.
Do we normalize it?
So no, we don't normalize, but that's a good point. Okay, it's averages, right? So let me put one. Yeah, let me normalize. No, we don't normalize. Yes, we do. Okay, 1/n. Okay. I'm just going to normalize by 1/n. So sometimes people normalize by 1/square root. Because then you would expect, like in normal situations, it's like a constant. If you normalize by 1/square root, then this object is a constant. But let's do this normalization, okay? Okay, so some properties. I don't want to erase this. Okay, properties. First, if f is a subset of G, then actually let's give a name to this. I'm going to say rad of G. I was told at some point recently that rad is like a slang word. I wasn't aware of this, but okay. I hope it's not anything that's not appropriate. No, actually, I'm these days you have to worry, so okay. Let's do r hat. Okay, so r hat is yeah. Really doesn't matter. Like whatever you do, you can translate one into another. This way, I can just write this as upper bound on what we wanted here without having some extra factors. Doesn't really matter. Yes?
Translation invariant measure.
Yes, yes. But, so let me do. Let's do a couple of things. So, if f is a subset of G, then r hat of f is smaller or equal than r hat of G. Now, what is the reason for that property? Anyone? Bigger set, yes. Max over a bigger set. 2. Let's take V, not new. Let's take let's say a U plus G, and let's look at. So I'm shifting, right? This is your question. I'm shifting the set by U. So what is R hat of U plus G? Okay, so what is going to happen here? To every vector in G, I'm going to add a U. So it's going to be epsilon G plus U. That's going to separate it into two products. And epsilon times U is going to come out of the max because it doesn't depend on G. As it passes through the expectation, what's going to get? 0. So it is translation invariant, but when you rotate, you might change things. Is that true? Actually, well, let's do it. I'll put it on homework. You can thank the guy in the last row. I mean, Gaussian is definitely rotation invariant. Okay, so what's another one? R hat of CG. If you scale things, right? If you scale your class, your set, then this is going to be equal to absolute value of C times R hat of G, right? If it's a positive constant, it will just come out, right? Now, what happens if it's a negative constant? Suppose C is equal to -1. So you're multiplying every G by a -1. But that's the same as putting a minus in front of the epsilon. But the distribution of epsilon and minus epsilon is the same. And you will use this fact for homework. So it's just epsilon, right? So nothing changed. And then C comes out, or absolute values. Okay. If there's another one before I get to a big one. Oh, okay, convex hull. So that's what was said here. R hat of convex hull of G is equal to R hat of G. Okay? And again, it's because maximum is attained at the corners, right? Okay, and the last one is the big one, which is super useful. By the way, all these properties that I'm putting down, if you learn them by heart, they make it really easy to analyze these Rademacher averages of various classes, neural networks, whatever you have, right? So they should be very natural, and then you can just play around with these different properties and get what you want. So here's one that's really is important and gets used a lot. So what I want to say is, let phi from R to R be L Lipschitz. So everyone knows what L Lipschitz is, right? So the phi of A minus phi of B is less than or equal to L times A minus B, right? then r hat of phi of g is upper bounded by L times r hat of g. So what is right? G is a vector now, right? And then you apply phi coordinate wise. Yeah? Is that definition clear? So you can think of a contraction as one example. So what is a contraction? It's a phi function that looks like this, let's say, right? Or maybe it looks like this. That's also a contraction. Maybe some of you recognize what this is. That's a contraction. If the slope is less than 1, it's a contraction. If the slope is more than 1, it's not, right? If the slope is 1 or less than 1, it contracts things, right? You put in something, you get something out something smaller. So what this is saying is the Rademacher averages of this contracted guy are smaller than L times the Rademacher averages of the not contracted guy, right? Which makes sense, right? Kind of like if you took your, what that thing is, and you kind of squished it, right? And then this notion of complexity should be smaller by that factor by which you squish it, right? Make sense? Okay. So this is really important. And what this allows you to do is to actually, when you look at a loss function composed with the class of functions, you can just get rid of the loss function if it's Lipschitz. So if you have like a hinge loss, and you're looking at Rademacher averages, we'll discuss later, of a hinge loss, just get rid of the hinge loss, right? Or absolute loss. Now with square, it's a little bit more complicated because square is not Lipschitz. So then you have to bound the domain, or you have to do something else, okay? Okay. And by the way, so the same property we're going to use for neural networks to get rid of the residue. That's exactly that. And then we'll play with some other properties to get sample complexity of neural networks. Okay. So, yes?
So can you elaborate why this 5 is true? I'm confused.
Why
5 is true?
Why 5 is true?
Yeah. So
How to prove it?
yeah.
The proof is, it will take me like 5 minutes. I can put it in the notes if you want.
So I guess the reason is I didn't get why the phi of G is a contraction.
So being Lipschitz is not necessarily the same as contraction. Contraction means that phi of 0 is 0, and then the Lipschitz constant is less than 1, right? That's a contraction. This is like a generalization.
Does it is it like related to the fact that the space of phi j is smaller than G or something?
Yeah, you can think of it as I don't want to say smaller, but think of it as a kind of taking this body and squishing it. So phi of G squishes the G, right?
In all directions?
Coordinate-wise, so
Okay.
per coordinate, right? Because every coordinate gets squished, right? Now, by the way, when you're gonna do, if you do contraction to get rid of the loss, you will have a different phi for each coordinate. But again, if each one of them is L Lipschitz, same result holds. So it doesn't have to be the same Lipschitz function on each coordinate. Okay? But that's kind of simple to understand. Okay? Okay. And the final thing, which is not really a property, but it's good to kind of know. I'm not going to put it as a property. So let's say it's A. If can you guys see here? if okay, maybe I put it there. If G is finite, then R hat of G is upper bounded by square root of log cardinality of G over N. Okay. How do you show this? So for those of you who know about what are sub-Gaussian random variables, these averages are sub-Gaussian random variables. So think of them as Gaussian. And the maximum of n Gaussians behave, or not n, cardinality of G Gaussians, maximum behaves like log, square root of log cardinality. Okay. So for a collection of independent, actually that doesn't matter. For a collection of say k Gaussian random variables, the maximum, expected maximum behaves like square root of log k. So that's kind of just a fact. Okay. There's some constant here that you can calculate easily using, let's say, Hofting inequality. In the homework, you will be using Hofting inequality, so I put the statement in there. So you'll learn how to do this type of stuff. Okay. So why are we talking about this object? Well, let me do just a few more things. Okay, sorry. Space. Okay. So consider a ball in n-dimensional space with respect to a p-norm. So what is a p-norm? A p-norm of a vector is 1 over p, sum over I from 1 to whatever the dimension is. Let's say it's n-dimensional. X lives in Rn. X I to the power of p. Okay? So, what is a unit ball? Unit ball is the set of all x such that the norm of x, the p-norm of x, is bounded by 1, right? So let me call that a unit ball. What is a unit ball with respect to Euclidean norm? A sphere. What is a unit ball with respect to L infinity norm? P is equal to infinity. It's a cube. What's a ball with respect to L1? It's this thing, right, that has 2n corners, right? Okay, so what is 2? Okay, now we're getting into slightly more complicated objects. Well, let's write out the definition. And you'll have to do something like this for the homework. So that's expectation with respect to all the epsilons. Max over G in this ball. And what we know is that its norm is less than 1. And let's put 1 over n here. Epsilon. Okay? So, how many of you know what a dual norm is? Maybe half of the class. Okay, so a dual norm let's say you have some norm. then there's a dual norm to that norm. So what is the relationship between them? It's very simple. The way that you define the dual norm for some vector y is just to take a max, or let's do sup to be proper, x, y, where you constrain the primal norm of x to be 1, right? So that defines the dual norm. Okay? So this is called LP norm. And what we know is that L2 norm is dual to L2 norm. L infinity norm is dual to L1 norm. And in general, LP is dual to LQ if 1 over P plus 1 over Q is equal to 1. That's the relationship. Okay? So you can get one from another. So it's like they meet at 2, and then if one goes up, the other one goes down. The one goes up from 2 goes much faster, of course. Right? Now, this is just a definition of the dual norm, right? Now, for L2, because we're considering L2, the dual norm is the 2 norm, right? So that's just 1 over n times expected 2 norm of a plus minus vector. So the Rademacher averages of a 2 norm ball is just how, what is the expected length of a vector from 0 to the vertex of the hypercube. But actually all of them are the same, right? And what's the length? So how far is, if I'm sitting at 0, how far is the vertex of a hypercube from me in n dimensions? Square root of n. So this thing is just square root of n. Now here's maybe a better way to write it. I'm going to say that's equal to 1 over n expectation of square root of a squared. I haven't changed anything. Right? Now, Jensen inequality tells me that I can put the square root out. So that's upper bounded by 1 over n square root of expected norm squared. I'm just helping you with the homework. See, the nice thing when you put this 2, and there is a 2 here, it's a 2 norm and you put the square. The nice thing is, it's just a sum of squares, right? And all the squares are that give you n, right? So now there is square root of n, and then there is 1 over n, so that's just 1 over square root. Yes. So that one is actually not an equality. When you pull the square root out, it's actually Jensen. There's a bit of, it's a small factor. I don't remember exactly the factor, but it's like it could be like square root of 2 or so. There's some extra factor that you get. Okay. All right. Yes.
So as for the definition of the dual norm, when you are considering the norm of x is smaller or equal to 1, which norm are you considering?
So this is the primal norm.
Oh, okay.
Yes.
Yeah, sorry, I'm really confused. I understand that the Jensen inequality is in general an inequality, but isn't here an equality here? Because epsilon always has the same length.
Oh,
I'm probably just really confused.
yeah, okay, fine, yes. Yes, you're right. So, sorry, you're right. It's equality just because they're all the same length. You're right, yes. I'm thinking of general random variables, in which case it's a really inequality. But again, the interesting thing is that then it's just like a small constant factor. Good, thank you. Okay. What else do I want? Let's see. How about can anyone do it quickly? I want to move on. This should be in the head calculation. 1/n? Yes? 1/n? So essentially you're going to pick that unit vector with one hot entry that gives you a +1 on the random sequence of epsilons, and that's 1. So it's 1/n. Do it at home. Okay, let me move on. Okay, so why? Yeah, I should be able to. I should be able to tell. Why do we care about this? Okay, so what I'm going to do is I'm going to now bring you back from this land of I just have a subset of Rn, right? And I'm going to tell you what is the subset of Rn that you need to consider. Now, this is my Calligraphic G, whatever it is, right? Is a set of functions from, I don't know, let's see, z to reals, right? These are functions. Okay, this is my Z space. Now, fix Z1 through Zn and look at the set G, which I'm going to define as, I'm actually going to write it as a calligraphic G projected onto Z1 through Zn. This is going to be my set. So what is the definition? It's just the set of G of Z1, Zn, or Zn, as G varies over a set G. And to be consistent with the previous notation, let's say the functions in G are bounded between -1 and 1, because that's how you're going to get that subset of -1 to the n, -1 to the 1 to the n hypercube. So this is a subset of -1, 1 to the n. Let me try to explain, right? So you go over the different functions, and for each function, you take a vector out. And you collect all these vectors, and that's your set G. Does that make sense? So you take one function, and then you evaluate it on all the points. Let's say there's Z1, Z2, up to Zn, right? They don't have to be sorted in this way, but just for visualization. So here's one function. This is, let's say, G1. This is the first value. This is the second value. This is the third value. And this is the fourth value, or the nth value. That is a vector. It's a vector of evaluation of this function on the set of data points. Is that clear? Now take G2. This point, that point, this point, that point. Okay? And so, okay, maybe I took a different one. You understand the idea? So as you go through the set G, calligraphic G, for each function you get a vector, collect all these vectors, and that's your subset of the hypercube. Clear? Yes.
Are you counting the ranges of these broken marks?
Yeah, so I'm assuming that, yes. Was that correct? Yeah. Then it's a true subset of -1, 1 to the n. In fact, this is not necessary. I did it just for simplicity, but you can think of R to the n. That's fine. So here's a really kind of a key result that makes your life really easy. So this is called symmetrization lemma. And the claim is that the expected max or sup over G in G, calligraphic G, of expected G of Z minus the average is upper bounded, and by the way, also lower bounded with a different constant, by 2 times expected over Z1 through Zn. So again, this is Z1 over Z1 through Zn, which should be clear because this is the only random variable here. Of through Zn. Okay? So once you've collected all these objects, all these vectors, you just need to measure on average how complex is this, how big is this projection?
The indirect petition is over the population.
Yes, yes, this is just over Z. And let me just write this out. This is nothing but, actually let me write out this part. Expectation over epsilon 1 through epsilon n, max over vector G in, now this is a vector, let me call it a different, let's say A in G projected onto Z1 through Zn of, and there is 1 over n, of A and epsilon, right? Or epsilon and A. Is it clear? So what the nice thing about this approach, I can let you copy that. Yes?
It's the assumption that the loss function is between -1 and 1.
Not important for this, no. Yeah. For any G. This requires nothing. And the proof is really 3 lines. It's 3 messy lines, so I put it in the slides, but you can read it if you want. But this is really a key, like if I had to stress something, it's really a key tool. If you need, like a bag of tools to do sample complexity or to analyze generalization and learning, this is the key step. Yes? Questions? Yes?
Why is it called a symmetrization model?
Yeah, because what you do is, if you look at the proof, you will see that you symmetrize. What you do is you say, I've got an unknown quantity because I don't know the distribution and the average. I'm going to replace this unknown entry by another sample drawn, another endpoints. But then, it really doesn't matter which one it is. I can swap, because they're all distributed, have the same distribution. I can swap any of them. But when I swap them, I'm just changing the sign for that entry. And that exactly gives rise to the epsilons. Okay? You'll see from the proof. Okay? Let me write this in another way. This upper bound is 2 times the expectation over data, Z1 through Zn. Expectation, I'm just going to write it as a double expectation, over epsilons, of max. Now, I'm going to go back to my G, and you'll see it's the same thing. G in calligraphic G, 1 over n sum of epsilon I G of Zi. And you see it's the same thing, right? Because that's another way to write it. And that's probably more what you will see in the literature. it's this form, but it's exactly that form, right? I'm just unrolling the definition of A in that set. Okay? Just copy them down, study them at home. They're the same quantities, right? So if there's anything that I want to convey to you in this lecture, it's the importance of this inequality. And the kind of why it's important is that now you can condition on the data and study the inner object. So what is typically done in calculations of sample complexity or learning to prove that you have some learning ability or generalization ability is to condition on the data and then compute what's inside. And let me just illustrate how amazingly powerful this is. By the way, just quickly, what is the r hat of Bn infinity? Not you. Someone else? 1, right? It just doesn't go down. So you see, like as the subset of the hypercube gets bigger and bigger, as it fills the inner space, it goes from 1 over n for the L infinity ball, for L1 ball, which is really tiny. L1 ball is really tiny. It looks big in one dimension, but in high dimension, it's really tiny. And then when you get to a round shape like L2, it's already 1 over square root of n. And then when it go further to fill the whole box, it becomes 1, which is not. So such things are not learnable, right? It doesn't improve with n. It doesn't improve with sample complexity. Anything in between, as soon as you can show that these random projections of the class onto the data do not fill up all the space, so you don't have all possible explanations of your data, right? That's the deal thing, right? Then you can say that you're doing learning, right? Okay, so example is very similar to the one that you're going to have for the homework. Is take a set F. Let me call it G. By the way, in the homework you'll see that the loss function being on top of your class, you can get rid of it. Especially the indicator loss is really easy to get rid of. That's one of the homework exercises. So, but let me take G, calligraphic G, to be the set of functions from Z to indicator that Z is larger than theta as theta varies over R, right? So these functions look like that. This is theta. Another one is like this, right? This is another theta. It's just the location of the theta that changes. These are the functions. Now, this is an uncountable collection of functions. So my uniform deviation, what I call uniform deviations, is this object, right? Expected, that one, right? Max over G in G, expected G minus the empirical G of Zi. By the way, it's common to omit the variable of integration. So what is this object? Well, it's max over, you can rewrite it as max over theta, right? Because that is the only variable that changes in my class of functions. So what is the expected function? It's the expected indicator. What's the expectation of an indicator? It's a probability, right? Probability that Z, my random variable, is larger than theta, minus the average of the indicators that Zi is larger than theta. Do you guys recognize this? This is the cumulative distribution function. I guess it's 1 minus. Is it z larger? No. Yes, it's 1 minus. Sorry. So if I flip the sign, you'll get the other direction, right? And this is the empirical CDF, right? So really, we're asking, can I just substitute the actual CDF with an empirical CDF? Anyone knows what that result is? Yes?
Something Cantelli, something.
Yeah, so it's called Glivenko-Cantelli result from the 1920s, and the quantification of this is due to Kolmogorov. Kolmogorov said, prove that this object is 1 over square root of n. Now, I think we can do it in, it's just Kolmogorov. We can do it in 10 minutes, right? So is it true that this one is 1 over square root of n? So we know that for any fixed theta, that's true by the law of large numbers. But is it true that for all theta, when I plot, sorry, it's 1 minus the CDF, so forgive me about this. It's like that. And like that, right? So is it true that they stay together all the time, right? For all theta. Right? That's the question. And if you remember, this is very much the question we asked for perceptron. Right? That was exactly the same. Is the empirical profile the same as the expected profile? And that's the question of statistics, right? Can you guarantee that empirical data tells you something about the unknown distribution, right? That is the crux of that question. Okay, now, I only have 10 minutes, so let's do the, let's turn to the symmetrization lemma. So I'm going to consider the red quantity for my as an upper bound. So consider a expected over epsilon 1 through epsilon. So this is 1 over n, and there is a sum of epsilon I indicator that Zi is larger than theta. These are my Rademacher averages. Should I write it higher? Can you guys see? Okay, write it higher. Okay. I'm putting 1 over n inside, it doesn't matter. So I indicator that Zi is larger. Now, the beauty of this is that Zi's are fixed. And I'm varying theta. So the space of theta is uncountable. But how many really different thetas are there? N plus 1. N plus 1. Yeah? The set G, so this G projected onto Z1 through Zn is actually finite. The cardinality of this set is at most n plus 1. It's equal to n plus 1 if all the points are distinct. But we know what happens there. It's upper bounded by square root of log cardinality, which is log of n plus 1. So up to log factor, we're done. We proved what Kolmogorov. Okay, I mean he did a bit more, but I mean essentially in the spirit it's the same type of thing that we did, right? And that log n can be removed through some more machinery, but it doesn't matter. So up to log factors. So you see that kind of the power. It's really the power that you can condition on the data, and look at the complexity of the set G for a fixed data. Right? And then there are other things like scale-sensitive dimension. There's some notion of a dimension of the class G. It's called fat shattering dimension occasionally, which tells you how complex the projection is. Okay? There are covering numbers that allow you to cover that set G. And by the way, that is if you know about covering numbers, it's just the number of balls that you need to cover the class, right? So if someone tells you, here is my class of function G, think of it like that, and I'm gonna try to cover this class G with balls, and then that's how many really distinct functions there are. Now what you can say is, well, I took the statistical learning class, and the professor told me that I shouldn't be looking at that. What I should be looking at is look conditional on the data, and now look at this set G, which is just a subset of Rn. Okay, and now cover that set. That covering is always finite. It's a n-dimensional object. Epsilon cover of that set is always finite, which is not true for the original set of functions. So don't try to cover. I mean, there are examples where maybe you want to cover in that space, but for this type of analysis, essentially in all the cases, you want to look at the projection onto the data, fix the data for symmetrization, and then look at the covering of this n-dimensional object. Okay? That's always finite. Any questions? Yes?
So I think, here what you are talking about is your condition on your data and try to see whether your model is generalized or not. So I guess this result is just specific for a set of data. If you change the training data, then your result will be changed.
Okay, so what happens with the data? See, the thing is, so there was a double expectation. And then there is this. So if, and then the Rademacher averages, right? If you consider this object, the Rademacher averages, by the way, sometimes it's called Rademacher complexity with some distinction, but let's forget about this. If you get an upper bound on this which does not depend on the data, that's fine. That's all, right? I mean, there's expectation sitting outside, it doesn't matter. If this is a constant, that's it. Now, you could get something, an upper bound here that actually captures some aspects of the data, of these data. And then you get expected complexity that actually depends on the data. And sometimes that's nice because you can say, well, not for all data things, this method will work. It will only work when the data are nice in a certain sense, right? And there are many of examples of that. So for instance, you get random data, and let's say the trace of the covariance matrix is small, then you get a result, and if it's not small, then so these would be called data-dependent bounds. So if you get an upper bound that depends on the data, that's a data-dependent upper bound. Okay. Any other questions? I think I've covered everything I wanted to cover. Let me just see if you can do the homework now. This you can do. This you should be able to do. This you can do. This you can do. Okay, so what is the convexity of a max? So max. So max of 1/2 of. So suppose you have max of some functional. Okay. Max of A plus B is upper bounded by max of A plus max of B. Yes? Everyone knows this? That's what I mean by convexity of the max, because if you put 1/2, understand. Okay. In particular, you can use Jensen inequality. When you pull expectation out from the max, you get an upper bound. through the max outside. But when you do it with the mean, it's the opposite direction. With the mean, expected mean is upper bounded by mean of the expectation. Yeah? This you can do, this you should be able to do. I think you're in it. Okay, see you next week.